Hello everyone, welcome to my talk. My name is Yichen Zhang from University of California, Irvine. Today I want to introduce Leaky DNN, stealing deep learning model secret with GPU context switching side channel. This work is collaborated with Junyi Wei, Professor Zhou from Fudan University, Professor Li and Professor Alfaruk from University of California, Irvine. And both Junyi Wei and Yichen Zhang are first author for this paper. Nowadays, deep learning models are being treated as highly valuable IP, since deep learning models are being applied in every corner of our daily life. It contains a large market size. For example, they have been widely used in the computer vision, speech recognition area, and also they show great power in embedded devices and data centers. However, designing a good deep learning model is very hard because some deep learning models have very complex structures. As this figure shows the structure of VGG16, which contains 13 convolution layers and 3 fully connected layers. And also, design a deep learning model with good performance requires great time and effort. Because deep learning model structure has a fundamental impact on its performance. This figure shows top 5 performance of ImageNet challenge. It took 4 years to improve the top 5 accuracy from 83% to 95%. When deep learning models are trained on the cloud, they are typically processed on the GPU because of the high performance of GPU. In the cloud setting, multiple users share the same physical GPU. The user can upload their deep learning models to the cloud and get a training output from it. But because of the isolation policy, all the users are isolated from each other. However, this also gives a chance for a spy user to co-locate with the victim user on the same GPU. Even though they are isolated with each other, the spy user can collect the GPU side channel leakage from other users. The key question we asked and aim to answer in this work is that, can an adversary infer deep learning models by exploiting GPU side channel? In previous work, there are several works utilizing side channel to steal deep learning model on the cloud, but most of them are CPU-based cache side channel. Only one work investigates GPU side channel. However, they can only infer the number of neurons of input layer. In their threat model, they firstly let CUDA spy co-locate with CUDA victim on the same GPU. By collecting the side channel leakage provided by GPU performance counter, they can infer the private information from the victim user. In their work, they manually switch on CUDA multiprocess service on the GPU to force co-location. The CUDA multiprocess service, which is MPS, will merge multiple processes into same context and send it to the GPU. But because of the scheduling of MPS, all the processes will be terminated at the same time. As a result, they can only collect one sample per DNN training iteration. However, in our work, we implement a default setting of GPU where the MPS is disabled. Each process will be cut into time slices and scheduled in a round-robin manner. This will cause a penalty when forced context switching between the processes. However, because of the context switching penalty, we can collect over 100,000 samples per DNN training iteration. Also, our work bypassed the patch provided by NVIDIA, which can block the GPU side channel leakage. We did a real cloud experiment on Amazon Web Service. By downgrading the GPU driver from patched version to unpatched version, the GPU side channel leakage can be accessed. Our work developed a new way of exploiting GPU context switching penalty. We are the first one to use the LSTM model as an inference model to infer the model secrets. Also, our work extracts the whole structure of deep learning models, including layer hyperparameters, and optimizer. Finally, our attack achieves high inference accuracy among a wide range of deep learning models. Our work experiments on NVIDIA GTX 1080 Ti, which is a popular GPU nowadays. When deep learning model is being trained on the NVIDIA GPU, the machine learning platform will translate the model structure into deep learning models operation sequence, and later it will invoke NVIDIA DNN library to trigger the hardware. Next, let's take a look at our attack framework, MOSCON. The MOSCON is short for the model secret extraction with GPU context switching. Before the actual attack, the adversary first provides a set of models to train the inference models. And then he or she will use the trained inference models to extract model secret of the victim deep learning models. However, there exist two challenges. Firstly, we can only collect uneven samples among deep learning operations. Also, the context switching side channel is weak. Therefore, we first launch slowdown attack on victim to extend the victim's execution time to obtain more samples per iteration. The approach is to launch multiple kernels inside the spy program, and our result shows that the victims can be slowed down 17 times. And also, we use the LSTM model as an inference model, because LSTM model can not only handle complex time series data, but also utilize the operation contextual information. The first step of our attack is to split iteration. Iteration is the period when you pass a batch of data through the deep learning model. In this step, we will classify the sample into NLP or Bayesian by light gradient boost machine. After that, the iterations will be splitted if the number of consecutive number is above the threshold. Next, we will try to recognize long DNN operations of convolutional layers and fully connected layers. Because convolution and matrix modification takes a long time to execute in these two layers, we built up an LSTM model as the inference model to classify each busy sample into conv, matmul, or other operations. After we handled all the long operations, we will try to recognize the rest operations of convolutional, fully connected, and max pooling layers, and classify each other operations into max pooling, ReLU, sigmoid, or bias add. Later, we will try to infer the hyperparameter for each layer. For example, we will infer the hyperparameters including filter size, number of filters, number of neurons, stride, and optimizer. Finally, we design a voting algorithm to combine the multiple predicted DNN operation sequence to correct the wrong predictions at each individual sequence. Here, we show 4 iterations of predicted operation sequence, and we correct several misprediction in each operation in each individuals by voting algorithms. And after that, we return the final operation sequence. Our attack achieved high accuracy among splitting iterations, operation inference, hyperparameter inference. Let's take a look at a case study on widget 16. For layer type and sequence, we only make one misprediction on one polling layers, and our accuracy can reach 95%. And for hyperparameters, our attack can achieve accuracy with over 92%. By extracting the most model secret of victim models, it can save a lot of time for adversary to design a good deep learning models. In the end, our work developed a novel way of exploiting GPU context switching penalty to extract the model secret of deep learning models. And we launched several slowdown attacks on victim user to improve the sampling rate. And we are the first one to design the LSTM-based inference model to extract the model secret. Finally, our attack can extract the entire model structure of the victim DNN models. In the future work, we will try to explore the potential defense methods. For example, we can launch several daemon processes which can detect anomalous GPU sharings. Also, we can develop some advanced GPU schedulers to protect the critical GPU applications, for example, the deep learning models. And that's the end of my talk. Thank you very much for your listening, and I'm very happy to answer your questions in the Q&A session.